Hello, everyone. Welcome to the session on fine tuning large language models with Snowflake Cortex AI. I'm Kala Govindrajan, Senior Data Cloud Architect in the Snowflake Innovation Showcase team. As businesses navigate the rapidly changing landscape of the digital age, the demand for innovative, efficient, and scalable solutions has reached an all time high. The accelerating pace of technological advancements, coupled with shifting market dynamics, means that companies must constantly adapt to remain competitive. Today, success hinges on not only on the ability to optimize operations, but also on leveraging cutting edge technologies and enhancing customer experiences with streamlining workflows. Today, I will walk you through an interesting journey of how leveraging AI, specifically large language models, and fine tuning techniques can lead to groundbreaking solutions tailored to your specific business needs. Today, we will explore and identify how large language models, in short, LLMs, can be tailored to fit specific business needs and scenarios, thereby enhancing efficiency, accuracy, and scalability in business operations. We will introduce and explore the capabilities of Snowflake Cortex AI and the benefits of using Snowflake for your AI needs. Then we will examine into the specifics of fine-tuning LLMs, techniques and strategies for fine-tuning LLMs, challenges in the fine tuning process, and the best practices for achieving optimal results. To demonstrate, we will show a specific application of AI in extracting medical codes, showcasing the practical use and benefits of LLMs in healthcare data management. Finally, we will share with you the performance of the fine tuned model against industry leading models. By the end of this presentation, you will gain insights into how, with Cortex AI, one can transform a generic LLM into a powerful assistant customized to solve specific business challenges. Let's embark on this journey to unlock the potential of AI in Snowflake through meticulous Cortex fine tuning. Snowflake Cortex provides end to end capabilities for developing and deploying GenAI applications. Now, let's drill down into what constitutes a LLM application or a GenAI application. Large language models have transformed the landscape of natural language processing and artificial intelligence. These models are trained on vast amounts of data to understand and generate human like text, making them incredibly powerful tools for a variety of applications. However, what if the goal is to customize the LLM to respond specifically to your data, analyzing documents and reports from your database, and also tailoring it to a specific task to meet a specific business need? We will analyze various techniques available to achieve this. The first and foremost is prompt engineering. When LLMs encounter questions involving unseen data, their performance can significantly improve through effective prompt design. Prompt engineering involves crafting the input, text, or prompt in a way that guides the model to generate the most accurate and relevant responses. By strategically adding context or restructuring the prompt, one can manipulate the model's focus and output with actionable prompt tuning template. And moving on, there is this exciting development of retrieval augmented generation. In short, we call it as RAG. RAG is a technique that combines the generative capabilities of a large language model along with embedding functionalities. It effectively expands the knowledge on the fly. And then there is fine tuning. Instead of providing explicit instructions, we give inputs and outputs as a supervised labels to the large language model and carry training. The last option is teaching the LLM from scratch, which is done in very rare scenarios. Now, how can you adapt LLMs to specific business use cases? Let's dive into each of the pros and cons and see which would be more apt for your business use case. So, with respect to prompt engineering, you do not really need any label data. You can just give instructions in plain text. The advantages of prompt engineering includes low resource requirement, which is it does not require any retraining of the model or altering the architecture, making it less resource intensive, and it has a lot of flexibility. You can quickly change the prompts and visualize what is the output in the application, and be employed directly on pre-trained models without any additional training or complex setup infrastructure setups that's required. The disadvantages, however, includes that there is a lot of dependency on the actual person who does the prompt tuning. The effectiveness of the prompt engineering highly depends on the experience of the user who's crafting the prompts. Also, the results can be very inconsistent and slight with even slight changes in the prompt. And this is limited by the model's knowledge itself. So the outputs are confined by what the model has already learned during its initial training phase. It cannot incorporate real time updates or external data not present in its training set. With respect to retrieval augmented generation, again RAG, which integrates a retrieval component into the generative process, the model retrieves essential or relevant information from a database or a knowledge base, which it then uses to inform its generated response. So you inherit the pros of the prompt engineering, and one additionally, you have this dynamic content getting integrated into your context. So you utilize the up-to-date data from your data sets, whether it is structured or unstructured. So RAG has that capability to improve over time as retrieval databases are updated. Now, there is the disadvantages includes a complexity in integration. Setting up a RAG system involves integrating a retrieval system with a generative model, which can be complex and resource intensive. There can also be latency issues. And also, at the end of the day, the quality of source data is very important. The effectiveness of the generated output heavily depends on the quality and the relevance of the data in the retrieval system. So, poor data quality can lead to inaccurate or misleading outputs. Finally comes fine tuning, which is very different from the other two. Teaching the model to do based on input and output examples is what is simply called as fine tuning. There is no explicit instructions required, and one optimal approach here is leveraging platforms, which is like Snowflake, that does not retrain all the model parameters. Instead, it does partial fine tuning. So instead of actually doing a full fine tuning, we use a pre-trained large language model and adopt techniques like low rank adaptation or LoRa, which freezes the pre trained model weights and injects trainable rank decomposition matrices into each layer of the transformer architecture. This greatly reduces the number of trainable parameters for downstream tasks. So, with just a few training examples, you can steer and achieve your task both accurately and efficiently. So, with fine tuned model, you get the pros of prompt engineering and retrieval augmented generation. Fine tuning requires relatively fewer data than training a model from scratch. Since the model has already learned general language representations during pre training, it can adapt to new domain specific tasks with a smaller amount of training data. It is less resource intensive and faster to fine tune a pre existing model than to train a new model from scratch. This makes advanced models more accessible to organization without vast computational resources. There is also a handling of very specific or domain specific tasks that is possible with fine tuning. And also, with respect to scalability, once a model has been successfully fine tuned, it can be scaled and deployed across various platforms and applications, maintaining consistent performance and adapting to various scales of data. So, fine tuning can be part of a continuous improvement strategy where a model is periodically updated with the new data to reflect recent changes or trends in the language or domain it serves. The only downside with fine tuning is it has an extra step, which is nothing but training. Let's dive deeper into what is fine tuning. The shorter definition of fine tuning involves retraining of model parameters to a specific business task. Say, for example, when you need to carry large scale pre training on general domain data and adaptations to a particular task or domain, then full fine tuning, which is nothing but retraining all the model parameters, becomes less feasible. So that is where you need to harness the potential of pre-trained large language models, and at the same time you want to enhance the performance for downstream tasks. So traditional fine tuning, which involves updating all the pre-trained parameters of pre-trained large models, which is time consuming and computationally expensive, needs to be avoided. So as the size of pre-trained large models continues to increase with billion parameters and computational resource requirements, there is a significant challenge. So what is instead done is something called as parameter efficient fine tuning, where you create customized adapters with the various techniques, and you can create a customized model that is specific to a task. So when do you want to fine tune? So if you don't want the high cost of training a large model from scratch but need better latency and results than your what you get from prompt engineering and retrieval augmented generation methods, then fine tuning an existing large model is an option there. So remember to note down the baseline performance of what you get from your prompt engineering and retrieval augmented generation before turning on to fine tuning so that you can do some benchmark comparison later. So now have seen what is fine tuning and what it allows to do and how it can adjust the behavior of the model itself. And techniques like parameter efficient fine tuning offers effective solutions by reducing the number of fine tuning parameters and memory usage while achieving comparable performance to full fine tuning. The demands for fine tuning pre trained large language models have led to a surge in the development of methods such as low rank adaptation or LoRa, which freezes the pre trained model weights as discussed before. So, with Snowflake, Cortex AI enables Snowflake customers to build a broad range of Gen AI applications, including text processing, generation, summarization, entity extraction, and classification systems. Now, if you look at Cortex fine tuning, it sits at the bottom right corner, which within the landscape of Snowflake Cortex AI. You're now going to see the perks of adopting the bottom right feature, where you can build your own tuned model with Cortex fine tuning from Snowflake, which is a fully managed service that lets you fine tune popular LLMs using your data and achieve the fewer trainable parameters and a highly training throughput, unlike adapters that has needs additional inference latency. We can make AI work for you by customizing AI to achieve the transformation. Cortex fine tuning is a low code or a no code workflow, and it is easy to customize AI with Cortex fine tuning. Let's dive deeper a little bit into this feature, which is Snowflake Cortex fine tuning. True that Snowflake Cortex puts LLMs and AI models in the hands of every user. And as a testimony for that is Snowflake Cortex fine-tuning, which is a fully managed service. The benefits of it includes it's easy to use. Users can fine-tune and use industry-leading LLMs very easily with SQL and or Python functions. You select a training data and optional validation data from your own data to fine-tune a foundational model. There is no data privacy or security concerns associated with data move or migration. Cortex fine tuning does automatic parameter efficient fine tuning without manual parameters. PEFT is a technique designed to fine tune models, and they are widely used. And when they are widely used, they are very effective. While full fine tuning of transformer based pre-trained large models involve training the entire model, including all layers and parameters on a downstream task, a PEFT can give you more advantages. Compared to fine-tuning a large model with billion parameters, using the Adam optimizer, LoRa, and PEFT techniques can reduce the number of trainable parameters by a factor of 10,000 and decrease GPU memory usage by threefold. LoRa achieves performance on par with or better than full fine tuning across models, and we'll see in action during the demo shortly. Snowflake Cortex fine tuning is serverless. There is no need to manage infrastructure when you build your own LLM apps. You can use the fine tuned model right after the completion of training, and no need to manage the deployment or purchase provisioned output through other vendors. The fully managed service abstracts all complexities associated with compute, memory, networking, and security. And what's new? We are adding many new models like Llama 3.1 for fine tuning. We are also adding features like model sharing across account and model replication cross region. And Cortex fine tuning is also going to be GA soon. Cortex AI serverless fine tuning and how to use this Cortex AI serverless fine tuning. You can select a base model and provide your training data set as part of the fine tune function or through a no code experience in Snowsight within Snowsight under Model Studio. Models available to fine tune are some of the popular ones like Llama 3.8b, Llama 370b, Llama 3.18b, Llama 3.170b, Mistral 7b, and Mistral 8x7b today. And there are more models getting added, and these are getting available in newer regions as well. After fine tuning completes, you can use the Cortex LLM complete function for instant reference. Just you have to swap out the base model with the fine tuned model. Here you will find an example of how the training data will have a prompt column that contains the prompts to the model and a completion column that contains the responses that the fine-tuned model is expected to produce. If your table or view does not contain columns with the required names, just use this column alias, and it is as simple as that. And this query is given as a parameter to the fine-tune function itself. So Cortex fine-tuning provides the most seamless and easiest way to get a fine-tuned LLM running with your data. However, there are certain scenarios where you may need a bit more control or flexibility over the fine tuning, and that's when you can leverage Snowpark container services for that. For example, fine tuning custom models not in Cortex, or customizing fine tuning parameters and strategies. For these scenarios, you can go to Snowpark Container Services and you can have more flexibility with your fine tuning strategy. Let us get into action. In this demo, we will take a hypothetical healthcare provider with thousands of patients who need to calculate patient risk scores. Additionally, they aim to streamline and optimize their claims operation process, which is currently managed manually by their support team and has been prone to errors. We will work on a public unstructured data set of health report documents. This data is already loaded into Snowflake stage, chunked for efficient processing, and it is now ready for fine tuning. Before getting into the details of how Cortex fine tuning can help with accurate and efficient medical ICD code extraction and processing, let us analyze at the business problem a little closer. In the complex landscape of healthcare, the accurate calculation of patient risk scores is not just a matter of compliance, but a crucial aspect that can significantly influence a provider's financial reimbursements capability. Accurate risk scoring is instrumental in ensuring that healthcare providers receive the appropriate compensation for the level of care they provide, balancing the dual objectives of delivering high quality care and maintaining financial viability. And these scores not only influence clinical decisions and resource allocation, but also significantly impact reimbursement rates from insurance companies. Given their importance, the need for precision risk score is important and cannot be overstated. Traditionally, healthcare providers have relied on various tools and methodologies to estimate patient risk scores. However, these conventional methods often fall short in addressing the complexity and the variability inherent in patient data. There can be discrepancies when extracting the ICD codes during claim reimbursements or doctor notes extraction, and this is where advanced technologies, particularly AI and machine learning, step in and transform this landscape. Now to the demo where I'll walk you through a Snowflake notebook in Snowsight. Large language model distillation focuses on replication or replicating the performance of a large model on a specific task by transferring its capabilities to a smaller model. This allows developers to achieve similar results to large models like GPT or Llama 405B, but with a reduced computational cost and faster performance through only for the targeted task. The process treats a large model as a teacher and the smaller model as a student. And this way, the student model could range from a simple logistic regression to a more advanced foundation models like BERT. By transferring essential knowledge from a complex teacher model to a smaller student model, the distillation flow preserves performance while reducing the size and the computational demands, making them ideal for integration across a broad range of devices and platforms. So now let's now jump into this medical extraction demo. The first step is prepare training and validation data. For this, leverage your existing data engineering pipeline to load the unstructured data or medical reports into a Snowflake stage. From this stage, we will fetch the file, chunk it so that the most relevant part can be extracted within a context window. That means how much text can be processed at once. So chunking ensures only relevant portions of a document are read or extracted, and this leads to improved accuracy. If your dataset is not in Snowflake database, please load training and the optional validation data files using one of the methods. Remember, fine tuning is only as good as the quality of the data provided. So the data set needs to be in appropriate format for fine tuning. The data set should contain fairly large quantities of high quality curated data. Now, once the data is available, we'll apply distillation flow, which begins with having the large language model label unlabeled data. Now, in this particular demo, I'm just importing the required packages here, and I'm setting the context in the cell. You can see that I have some data in this table already loaded, and the reports, the file and the content is available here. I have some certain number of samples data here. I'm going to use that and first use the large language model, in this case, which is Llama 3.1405B, and create a labeled data set for the distillation flow. As you can see, my create table, I have already created a table called Llama output ICD, and using the document text, which is nothing but all the reports chunked already in this column, I'm uh, doing some kind of prompt engineering, asking Llama 3.1405B to give me those training samples, and have asked it to extract the ICD code in this particular format. So the output that you see is a labeled data set, which can now be used to train the student model. This has learned already from the teacher, and you can see the output ICD codes in a Python list form. We will be splitting the data sets into training, validation, and test. Before moving on to fine tuning the model, we will leverage a small model to compare how it performs on par with the fine tuned model. I have used a Llama 3 8B for extracting the code using the same prompt and also asking it to append the ICD codes or extract the ICD codes from the larger model on the same data set. The output of this can be observed here. And as you can see, what you see is two columns here. The one on the left, which is AI ICD code, is the output from my large model, and which is nothing but the ICD codes extracted from a large model. And the one on the right shows the model output from my smaller model, which is Llama 38B. As you can see, there is some discrepancies. Here you have 66 dot E66.01 and you have E66.0, which is a more generic version, and similarly in this case as well. So now we will be doing the accuracy or benchmark comparison towards the end. First, let's go ahead and fine tune the same Llama 38B with Cortex fine tuning. So we have created the validation, training, and test data set. And in order to create this production ready application, we have to test the accuracy. The Cortex fine-tuning function helps us creating a fine-tuning job. The tuned model is saved to the model registry in this on the schema itself. You pass these parameters, which is nothing but first is the create, and you can choose a base model, which is Llama 38B in this case. You can choose an identifier. I want to call my fine-tuned model as fine-tune Llama 38B ICD codes built. And then I give up a training data query wherein I specify what is my prompt and what is my completion. Please note that the completion or is the response what the large model generated, and also I give a validation data set. Now I can give a name for this particular fine tuning model, and I can wait for a minute. It takes few minutes for the whole process to complete, but I can observe the workflow or the status by copying this. So as you can see, I have a certain number of output or parameters that's being returned. What model, base model that I have used for Cortex fine tuning, when was this created, what is the timestamp, and then what is my fine ID identifier of the new model that I am creating, or the job ID itself. Actually, in this case, like how much progress has happened, what is the status of the fine tuning workflow, and what is my training data query, and what is my validation data query. And then you can also see what is the result when the fine tuning actually completes. Now let's, it takes few minutes, so go and grab a cup of coffee while the fine tuning workflow would be done. But in this case, I'm so excited and I want to use a previously leveraged fine tuned model and show you the accuracy and outputs from what the fine tuned model does. So now what I do is I have a previously created fine-tuned model. I'm using that fine-tuned model, and in this case, I'm not even sending any prompt or anything to my complete function for inference. Instead, I just use the model, uses a data set from my test data set, and want to carry inference. Right. So I'm creating this table called Llama 38B ICD codes, which is my new table created based on the fine-tuned model outputs. Now this is already created, so what I can see is I can just load it into a data frame, pandas data frame, and I can see my output here, and this is returned in a Python list, and we can quickly validate whether how accurate this is. Now we can let's don't forget that we have also extracted the codes from the smaller model, the base model itself, and that we can store it in another table so that we can do an accuracy evaluation in the same time. And you know that the this particular table contains both the output from the large models as well as a small model for a side by side comparison. Now I have a reg expression function here, which actually compares extracts all the ICD codes, and it compares the list, the both Python list. And you can see that, like, my ICD codes from my Llama 405B, which is the large model, and the fine tuned one match. To calculate the actual percentage of accuracy, I'm going in and row by row, I'm calculating what is my cumulative accuracy. And you can see that with the fine tuned model, I have achieved 100% accuracy with my fine tuned DF. In the case of my the small model itself, you can see that the accuracy is low as 6%. And this brings us to the end of this notebook. So clearly, with Cortex fine tuning, we can it is as simple as that. If there is a task you want to achieve and tailor it to your business needs, you need to just pick a small business model, carry distillation flow, and create a training data set based on a large model. Pick a small model for Cortex fine tuning and push it through this workflow. This can be also done through the UI in far lesser steps. That brings us to the end of this notebook. And we undoubtedly, healthcare providers and medical coders now extract these patient risk scores accurately. There is a quick Streamlit app that you could visualize these the outputs. So because I'm able to extract the ICD codes accurately, now healthcare providers or even claim reimbursement or reimbursement providers can come and look at each of the patient they wish to see, and understand what are the different ICD codes which has been extracted from Snowflake Cortex fine tuning. These are accurate, 100% accurate as seen in the evaluation before. And they can understand what is the risk score associated with each patient. Also look at the data reports or the unstructured data reports. This is being loaded into Snowflake. Let us look at some benchmarking results. The results from fine tuning demonstrated that the accuracy achieved with the fine tuned model matched that of the large base model. In contrast, the smaller model, which is Llama 38B, reached only 6% accuracy, clearly indicating that the fine tuned model is ready for a production deployment. When looking at the cost, the results from fine tuning demonstrated significant cost effectiveness because it achieved the same accuracy as that of a larger language model, which is 8x times more costlier. And last but not the least, the throughput. Not only that the fine tuned model delivered better or equal results, but it also delivered a higher throughput overall. And in conclusion, reduces expenses when building production ready AI applications for more specialized tasks. In this quick demo, we saw that how easily fine-tuning elevates the workload on physicians and medical coders as we aim to advance the implementation of autonomous medical coding. This approach will not only ensure high accuracy and clinical specificity, but also support various healthcare models, paving the way for more sustainable and effective healthcare environment. Also, you can see the ability to adopt fine tuning techniques from Snowflake, which enables a team to start with a small off the shelf model and customize the model to overarching goal for enhancing efficiency and enhancing 100% accuracy at very lower cost. Try Cortex fine tuning today. We have new models getting added and coming in new regions as well. There are various tutorials in quick snowflakedevelopers.com website, and which you can leverage for your self study. I hope you enjoyed the session. Try Cortex fine tuning, which will be GA soon. Thank you.